Module 29, Lecture B, Regression Clustering. By the end of this lecture, you will be able to evaluate regression models using scale-dependent and scale-independent metrics, evaluate clustering results using internal and external metrics, and use dummy classifiers and regressors as baseline comparisons. Regression metrics. Explained variance. Explained variance shows how well a model captures the overall movement and variability in data, not just how close its predictions are on average. In electricity demand forecasting, for example, it reflects how well the model follows seasonal changes. A high value means the model captures important patterns, while a low value means much of the data's variation is missed. Explained variance measures how much of the target's variability a model captures, without depending on the target's units. This makes it useful for comparing models across different contexts, unlike error metrics such as mean absolute error or root mean squared error. However, it does not show the typical size of prediction errors, so it reflects captured variation rather than everyday prediction accuracy. Explained variance helps describe how well a model fits the data, but it should not be judged alone. A model can explain a lot of variance and still make important errors, while a model with modest explained variance may still be useful if it improves on a simple baseline. To assess real value, compare it with a basic reference model, and consider error metrics and domain knowledge. Python code explained variance. This example shows how explained variance is used in regression by comparing how much variation the model captures with the size of its errors. It highlights why different metrics are useful together when evaluating model performance. We import NumPy to work with numerical data arrays and use Scikit-Learn's metrics tools to evaluate regression models. In particular, the explained variance score shows how well a model captures variation in the target values, while mean absolute error measures the average size of prediction errors. An array is created with NumPy to store the actual electricity demand values in megawatt-hours as floating point numbers. These values provide the baseline for comparing prediction models later. Shifted predictions are created by adding 30 to each actual electricity demand value. This simulates a model that follows the overall demand pattern but consistently predicts too high by a fixed amount. It helps evaluate whether the model captures the rises and falls in the data, even with a constant offset. We create a NumPy array of model predictions where every time point is assigned the same value, 150. This flat forecast ignores changes in actual demand, so it cannot follow the data's rises and falls. The example shows that a model may have a similar average error to others, while still missing important variation. The code first verifies that the shifted predictions and actual demand values have matching shapes, so they can be compared correctly. If they do not align, it raises an error to stop the process. This check helps prevent later calculation problems caused by incompatible data. Before comparing predictions with actual demand, the code checks that both arrays have the same shape and number of values. If they do not match, it raises an error to signal the mismatch. This validation helps prevent incorrect calculations by ensuring the data is consistent. We use Scikit-Learn's explained variance score to compare two prediction sets for electricity demand. The shifted predictions are evaluated on how well they follow the actual rises and falls in demand, while the flat predictions are tested as a non-varying baseline. This comparison shows which predictions better capture the patterns in the data. We compare both the shifted and flat predictions against actual demand using mean absolute error. This measures the average size of each model's prediction errors, showing how far the forecasts are from the real values on average. The calculation uses Scikit-Learn's mean absolute error function to summarize prediction accuracy by error magnitude. The code reports the scikit-learn version for reproducibility, then compares shifted and flat models using two metrics. Explained variance, shown to 2 decimal places, indicates how well each model captures variation in the data and has no units. Mean absolute error, shown in megawatt hours, gives the average prediction error size for each model. This example compares 2 electricity demand prediction models, using explained variance and mean absolute error. The shifted model is consistently too high, but follows the demand pattern well, so it gets a stronger explained variance score. The flat model stays constant, and although its average error is similar, it does not capture the trend as well. Together, these metrics show that explained variance measures how well predictions follow variability, while mean absolute error measures the average size of mistakes. Absolute error metrics. Absolute error metrics measure how far predictions are from actual values in the target's original units, making them easy to interpret. Mean absolute error is a common example, showing the average size of prediction errors without considering whether they are too high or too low. This makes absolute error useful for explaining model performance clearly, especially to non-technical decision makers. Absolute error metrics depend on the scale of the target variable, so their values only make sense within a specific context. This makes them useful when the units are meaningful, but not suitable for comparing problems with different ranges or units. Always interpret these errors by considering the typical size of the target and the real-world impact of being wrong. Absolute error metrics give a stable, easy-to-interpret view of prediction accuracy because extreme errors do not dominate them as much as squared error metrics. This makes them useful when outliers or rare cases could skew results, such as unusually high electricity use. However, they may understate problems when large errors are especially costly, such as in hospital demand forecasting. For that reason, they are often used with other metrics to balance clarity with sensitivity to big mistakes. Python code, absolute error metrics. This example evaluates predictions using absolute error. Mean absolute error reports the average error in the original units, making it easy to compare the model's performance with a baseline. We import the main tools needed for a simple regression workflow: NumPy for numerical work and Scikit-Learn for machine learning. From Scikit-Learn, we use a dummy regressor as a baseline. Linear regression is the main model, mean absolute error to measure performance, and a train test split to evaluate the model on unseen data. We define 2 NumPy arrays to store a small housing dataset, one for house sizes in square meters, and one for the matching prices in thousands of dollars. Keeping the data directly in memory makes the example simple and lets us focus on the main concepts without dealing with large datasets. The house size data is reshaped into a 2-dimensional form because Scikit-Learn expects features in that structure. The reshape method lets the number of rows be inferred automatically while creating one column. The house prices are then set as the target values, keeping each price matched with its corresponding house size for training and evaluation. The code first checks that the number of house sizes matches the number of prices. If they do not match, it raises an error, because each input must have one corresponding target value. This validation helps prevent data mismatches that could cause problems during model training and evaluation. We split the house size and price data into training and testing sets so the model can be evaluated on examples it has not seen before. Using Scikit-Learn's train test split function, 30% of the data is reserved for testing, and the remaining 70% is used for training. A fixed random state makes the split reproducible each time the code runs. The result is separate training and testing subsets for both the features and the target values. We create a linear regression model with Scikit-Learn to find the best fit line for the training data. After fitting it to house sizes and prices, the model learns the relationship between size and price by choosing coefficients that reduce the gap between predicted and actual prices. To create a simple baseline, we use a Scikit-Learn dummy regressor that always predicts the average target value from the training data. After fitting it on the training features and targets, the model uses that mean for every prediction. This gives us a basic benchmark for judging whether more complex models perform better. We now predict prices for the test houses that were not used during training. The linear regression model estimates prices from the test features, while the baseline model predicts the training set average for each house. Comparing these results shows whether linear regression improves on a simple average-based prediction. We use mean absolute error to compare the linear regression model with a simple baseline. The model's error is the average absolute difference between the actual test prices and its predictions. The baseline is evaluated the same way, using predictions based on the training data's mean price. This shows whether the regression model performs better than a basic average-based prediction. The output first shows the Scikit-Learn version to support reproducibility. It then compares the linear regression model's mean absolute error with a simple baseline that predicts the training average. Finally, it displays the actual price of one test house and the model's predicted price, making it easy to judge how close the prediction is. This script compares a linear regression model with a simple baseline for predicting house prices from house size. It trains both models, tests them on held-out data, and uses mean absolute error to measure how far their predictions are from the actual prices on average. It also prints the Scikit-Learn version and shows one example prediction. The linear regression is expected to have lower error than the baseline, showing that it captures the relationship between size and price more effectively. Percentage log errors. Percentage and log-based error metrics judge regression predictions by how large the error is relative to the true value, rather than only by the number of units missed. This makes errors easier to compare across different scales, such as small apartments and large factories. By focusing on proportional error, these metrics show whether a model's mistake is small or large in context. Percentage error measures show prediction errors relative to actual values, which makes them easy to interpret in areas like business forecasting and finance. However, they can become undefined or misleading when actual values are zero or very small. They also may not capture the real business cost of different errors, such as overestimating versus underestimating demand, so their results should be judged in context. Log-based error metrics measure prediction errors on a multiplicative scale, making them useful for data that varies across very large ranges. They can reduce the influence of extremely large values and show whether model accuracy is consistent across scales. However, they require care, because logarithms cannot handle negative values and need special treatment for zeros. Together with percentage errors, they complement scale-dependent metrics by giving a broader view of model performance. Python code, percentage log errors. Compare percentage and logarithmic regression errors to understand how different metrics describe model mistakes. Relative metrics are useful because they show errors independently of scale, and printed results can reveal how each metric behaves differently. We import NumPy to handle arrays and numerical calculations efficiently, and use Scikit-Learn to access error metrics. The mean absolute percentage error measures the average percentage difference between predictions and true values, helping assess proportional error. The mean squared log error measures squared differences on a logarithmic scale, which is useful for relative errors in data with large ranges or exponential growth. We define two NumPy arrays, one for the actual positive values and one for the predicted values to compare against them. Keeping the true values positive is necessary for percentage-based and logarithmic metrics. Both arrays use floating point numbers to support precise calculations. Before computing the metrics, the code checks that all true values are positive and all predicted values are not negative. This is required because percentage and logarithmic error measures are only valid under those conditions. If the data violates them, the code raises an error so the user can correct the inputs. To measure prediction error, first find the absolute difference between each true value and its prediction, which shows how far off the prediction is regardless of direction. Then convert each error to a percentage by comparing it with a true value and multiplying by 100. This gives a relative measure of error, making it easier to judge the size of mistakes across different scales. Mean absolute percentage error shows the average prediction error as a percentage of the true values, making it easier to judge error relative to scale. Root mean squared logarithmic error compares predicted and true values on a logarithmic scale, highlighting relative differences and working well for data with large ranges or exponential growth. The code reports the Scikit-Learn version for reproducibility, then prints the true and predicted values in a readable integer format. It also shows the absolute and percentage errors to compare predictions with the true values. Finally, it summarizes model accuracy using mean absolute percentage error and root mean squared logarithmic error. This script compares percentage-based and logarithmic regression errors for true and predicted values. It first ensures the values are valid for these metrics, then contrasts absolute errors with proportional percentage errors. It reports mean absolute percentage error, or MAPE, and root mean squared logarithmic error, or RMSLE, which both help evaluate prediction quality in a scale-independent way. Clustering metrics. Median quantile deviance. Median quantile deviance evaluates how well clusters represent their typical members, especially when data is skewed or contains outliers. By focusing on median-based distance from the cluster center, it is less affected by extreme values than average-based measures. In customer spending data, for example, this helps prevent a few very high spenders from distorting the assessment of typical behavior. Median quantile deviance is a robust way to judge whether a cluster truly represents its typical members. It looks beyond simple closeness to the mean, which can hide variation or be distorted by outliers. A high deviance suggests the cluster's central pattern is not well captured, so the clustering may need to be reassessed. Median quantile deviance shows how closely observations match their cluster's typical profile. Lower values suggest tighter clusters, while higher values indicate more variation. However, it should not be used alone, because it can favor many small clusters that may not be useful or interpretable. It is most valuable when combined with visual checks, domain knowledge, and external validation to ensure clusters are both statistically sound and meaningful. Python code. Median quantile deviance. This example evaluates clustering compactness in a way that is less affected by outliers. It uses median deviance to focus on typical cluster tightness, where lower values mean the clusters are more compact. We import the main tools needed for clustering analysis: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, we use the KMeans clustering tool to group data points by their features, and the blob dataset generator to create synthetic clustered data. Together, these imports prepare us to generate, visualize, and analyze clusters. We generate synthetic data with Scikit-Learn's make blobs function to create 120 samples in 3 clear clusters. A moderate cluster spread keeps the points fairly tight, and a fixed random state makes the results reproducible. This controlled dataset is used to test clustering methods, with a few unusual observations added later. We create a small set of outliers with coordinates placed far from the main clusters, then add them to the existing dataset. Including these extreme points lets us test how robust the clustering algorithm is when it encounters unusual data. A K-means model is created with 3 clusters, using a fixed random state for reproducibility and multiple initializations for more reliable results. The model is then fit to a dataset containing both normal points and outliers. During fitting, each point is assigned a cluster label, allowing us to assess how well KMeans handles the data in the presence of outliers. Count the observations assigned to each of the 3 clusters, making sure every cluster has a recorded size. Then check whether any cluster has no observations. If one is empty, raise an error, because valid clustering results require each cluster to contain at least one data point. To evaluate the clustering, each data point is matched with its assigned cluster center, using the labels from the K-means model. Then, the Euclidean distance between each point and its center is calculated. These distances show how closely the points group around their centers, helping assess the quality of the clustering. To summarize cluster distances, we use 3 deviance measures. The mean deviance gives the average distance from points to their assigned cluster centers, but it can be influenced by outliers. The median deviance gives a more robust typical distance, while the upper quartile deviance shows how far the more distant quarter of points are from their centers. The output first reports the Scikit-Learn version to support reproducibility. It then summarizes cluster compactness using 3 distance measures: the mean distance to each assigned cluster center, the median distance for a more outlier-resistant view, and the 75th percentile distance to show how far most points are from their centers. The visualization begins by setting up a matplotlib figure, then plots a histogram of the distance values using 14 bins. The bars are styled in steel blue with white edges for readability. 2 reference lines are added, a dark orange line for the median quantile deviance and a dashed black line for the mean deviance, making it easy to compare the 2 measures. The visualization is titled to show that it summarizes distances within assigned clusters. The x-axis represents each observation's distance from its assigned cluster center, while the y-axis shows how many observations fall within each distance range. A legend distinguishes the median quantile deviance from the mean distance, and the plot is then displayed for analysis. This script shows how to assess K-means cluster compactness when outliers are present. It creates 3 clusters with outliers, assigns points to 3 groups, and measures each point's distance from its cluster center. The key comparison is between the mean distance, which can be pulled upward by outliers, and the median distance, which is more stable. It also reports the 75th percentile and uses a histogram to show how the mean and median differ in sensitivity to extreme points. External cluster validation. External cluster validation checks whether clusters found by an algorithm match trusted outside information, such as known classes or expert labels. For example, patient groups based on symptoms could be compared with confirmed diagnoses. The goal is to judge whether the clusters reflect meaningful real-world categories, not just whether they look compact or well separated. External validation metrics compare clustering results with known reference labels to see whether similar observations are grouped consistently. Common measures include adjusted RAND index, normalized mutual information, homogeneity, completeness, and V-measure. Together, they show whether clusters match true classes, whether each cluster is focused on one class, and whether each class is kept together, helping evaluate how well the clustering captures meaningful structure. External cluster validation compares clusters with known labels, but those labels may not fully match the structure the clustering is meant to reveal. A low score can mean the clusters capture a different but still useful pattern, especially in exploratory work. These metrics are most helpful when the expected categories are well defined, and they should usually be interpreted alongside internal metrics and expert judgment. Python code. External cluster validation. This example evaluates clusters by comparing them with trusted labels. External metrics focus on how well the clusters match the labels, ignoring the arbitrary names or numbers assigned to clusters. Higher scores mean stronger agreement. This setup imports the main Scikit-Learn tools needed for clustering the iris dataset. It uses KMeans to group similar data points, loads the iris flower data with true species labels, and brings in evaluation metrics to compare the clusters with those labels. It also imports a standard scaling tool, so the features are normalized and contribute more evenly to the clustering process. We load the iris dataset from Scikit-Learn, which contains flower measurements and their species labels. The measurements are used as the input features for clustering, while the true species labels are kept separately to evaluate how well the clustering results match the actual flower types. Before clustering, confirm that the feature data and labels have the same number of rows. Each data point must match one label, and if the counts differ, the program raises an error. This check protects data integrity and helps prevent problems later in the clustering process. Before clustering, the features are standardized so they contribute on the same scale. A standard scaler removes each feature's mean and scales it to unit variance, producing values with a mean of 0 and a standard deviation of 1. This step is important for KMeans because the algorithm is sensitive to differences in feature scale. We configure KMeans to form 3 clusters because the iris dataset contains 3 species. A fixed random state makes the results reproducible, and running multiple initializations helps choose the clustering with the lowest inertia. The model is then fit to the scaled iris features, assigning each data point to a cluster, so the labels can later be compared with the true species labels. To evaluate how well the clustering matches the known labels, we use several standard metrics. The adjusted rand index measures label agreement while accounting for chance, and normalized mutual information measures shared information between the true labels and clusters. We also compute homogeneity, completeness, and the v-measure, which together show whether clusters contain single classes, whether each class stays in one cluster, and how well these two goals are balanced. We first note the Scikit-Learn version to support compatibility and reproducibility. Then we evaluate KMeans clustering by comparing its cluster assignments with the true labels using several scores: adjusted rand index, normalized mutual information, homogeneity, completeness, and v-measure. Together, these metrics show how well the clusters match the known classes, even though KMeans did not use those labels during clustering. This script tests how well KMeans clustering matches the known species in the iris dataset. It scales the features, forms 3 clusters without using the labels, and then compares the clusters to the true species. Metrics such as adjusted rand index, normalized mutual information, homogeneity, completeness, and v-measure show how closely the unsupervised clusters align with the actual labels. Internal cluster metrics. Internal cluster metrics evaluate clustering quality using only the data and the assigned clusters, so they are useful when no labels are available. They measure whether similar observations are grouped together and different ones are kept apart, helping compare methods, cluster counts, or pre-processing choices. These scores are helpful guides, but they do not prove that the clusters are meaningful or useful in the real world. Clustering quality can be evaluated with several metrics. The silhouette score measures how well points fit their own cluster compared with nearby clusters, where higher is better. The Davies-Bouldin index favors lower values, showing clusters are less similar to their nearest neighbors. The Calinski-Harabasz index favors higher values, indicating stronger separation between clusters compared with variation inside them. Together, these metrics help choose a good number of clusters, though each emphasizes a different aspect of quality. Internal cluster metrics are useful, but they have important limits. They work best when clusters are compact and clearly separated, and can be misleading for elongated, uneven, or outlier-affected data. Because results also depend on feature scaling and data preparation, these metrics should be combined with visual checks, domain knowledge, and practical interpretability to judge whether clusters are truly meaningful. Python code, internal cluster metrics. This example compares internal clustering metrics to help choose a good clustering result. Clusters that are compact and well separated should receive better scores, and the printed results guide the selection. We import key Python tools for a clustering workflow: NumPy for numerical computing and Scikit-Learn for machine learning. From Scikit-Learn, we use KMeans to form clusters, a synthetic data generator to create clustered data, and several scoring metrics to evaluate clustering quality. We also use a standard scaler to put features on the same scale, which helps distance-based clustering and evaluation work properly. We create a synthetic dataset with the Scikit-Learn make blobs function, which generates points arranged in natural clusters. In this example, it produces 300 data points grouped into 3 clusters, with a moderate spread around each center. A fixed random state makes the results reproducible, so the same dataset is created each time. This controlled setup is useful for testing clustering algorithms. Before clustering, the code verifies that the dataset has 300 rows and 2 features. If the data does not match this expected structure, it raises an error. This quick validation helps catch formatting problems early and prevents issues later in the analysis. Before clustering, features should be put on a similar scale, so distance-based methods like KMeans are not distorted by different units or ranges. Standard scaler does this by centering each feature around its mean and scaling it to unit variance. After applying its fit and transform process, the data is standardized and ready for clustering. The code first displays the Scikit-Learn version to confirm compatibility and available features. It then prints column labels for comparing clustering results, including the number of clusters and 3 evaluation scores: Silhouette, Davies-Bouldin, and Calinski-Harabasz. We compare K-means clustering with 2 through 5 clusters by fitting each model to the scaled features and predicting labels. For each option, we evaluate performance using 3 internal metrics: Silhouette score, Davies-Bouldin score, and Calinski-Harabasz score. Higher Silhouette and Calinski-Harabasz values and lower Davies-Bouldin values indicate better clustering, so printing these scores helps compare the cluster choices clearly. To judge clustering quality, look for higher Silhouette and Calinski-Harabasz scores, which suggest clearer, better defined clusters. A lower Davies-Bouldin score is preferred because it indicates stronger separation between clusters. Comparing these metrics across different cluster counts helps choose the best number of clusters. This script compares K-means clustering results using internal evaluation metrics. It creates a dataset with 3 natural clusters, scales the features, and tests cluster counts from 2 to 5. For each option, it reports Silhouette, Davies-Bouldin, and Calinski-Harabasz scores. Better clustering is indicated by higher Silhouette and Calinski-Harabasz scores, and a lower Davies-Bouldin score, helping identify the most suitable number of clusters. Baseline comparisons. Dummy classifiers. A dummy classifier is a simple baseline for classification tasks. It does not learn patterns from data, but instead uses basic rules such as predicting the most common class or guessing randomly. This helps show whether a real model is actually learning something useful. For example, in a medical dataset with mostly negative cases, always predicting negative may look accurate, while still missing important positive cases. Dummy classifiers provide essential baselines for imbalanced datasets, where high accuracy can be misleading. For example, in fraud detection or churn prediction, a model may simply predict the majority class and miss the cases that matter. Strategies such as most frequent, stratified random, or uniform random baselines help show whether a real model performs better than simple chance or majority class behavior. Evaluate dummy classifiers with the same metrics used for real models, not accuracy alone. Measures like precision, recall, and F1 score reveal whether a baseline is hiding poor performance, such as missing many spam messages while predicting most messages as not spam. Comparing against this baseline helps show whether a model is truly learning. And if it only slightly improves on the dummy classifier, it may need better features or a stronger algorithm. Python code, dummy classifiers. Compare real classifiers with simple dummy baselines to check whether they are truly learning. Dummy strategies can expose misleading accuracy, especially with imbalanced data, and show whether a model performs better than trivial guessing. We import key Scikit-Learn tools for building and evaluating a simple classification workflow. These include a function for creating synthetic classification data, a dummy classifier for a baseline, and logistic regression for binary classification. We also use accuracy and balanced accuracy to measure performance, and a train test split tool to evaluate models on unseen data. We create a small, imbalanced classification dataset using Scikit-Learn's make classification function. It contains 1,000 samples with 6 features, 3 of which are informative. The class split is set to 90% versus 10% to create imbalance, and a fixed random state makes the results reproducible. The code first verifies that the feature data and target labels have the same number of rows, so each input has a matching label. If they do not match, it raises an error. This check helps prevent misaligned data, which could lead to incorrect model training or evaluation. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 30% of the data is reserved for testing, while stratification keeps the class distribution consistent in both sets. A fixed random state makes the split reproducible across runs. We create a small set of models to compare simple baselines with a real classifier. 2 dummy classifiers provide baseline predictions. One always chooses the most common training class, and the other samples classes according to their training distribution. A logistic regression model is added as the stronger learning method, with settings chosen to support convergence and reproducible results. The code checks the Scikit-Learn version, then evaluates each model in a collection using the same training and test data. Each model is trained, used to predict the test labels, and scored with both accuracy and balanced accuracy. Balanced accuracy is included to better reflect performance when classes are imbalanced. The results are printed with each model name and the 2 scores rounded for readability. This example compares real classifiers with simple dummy baselines on a small dataset where one class makes up most of the samples. It evaluates 2 dummy strategies and logistic regression using both accuracy and balanced accuracy. The key lesson is that high accuracy can be misleading on imbalanced data, because a model that mostly predicts the majority class may still look successful. Balanced accuracy reveals this weakness, while logistic regression should perform better by learning patterns beyond simple guessing. Dummy regressor baselines. A dummy regressor is a simple baseline for regression tasks. Instead of learning patterns, it predicts using a basic rule such as the average or median of the training data. This lets you check whether a more complex model is actually useful. For example, if a model predicting household electricity use cannot beat the average consumption, it may not be adding value. Choose a dummy regressor baseline based on the target distribution and the metric you care about. The mean works well for squared error, while the median is more robust to outliers. A fixed business-based value can also be useful. Comparing your trained model with these simple baselines using errors such as mean absolute error or root mean squared error helps show whether the model is truly learning better patterns than a basic guess. Dummy regressors provide a simple baseline, especially when the target changes little, the dataset is small, or the task is difficult. They show whether a model is learning useful patterns or only matching common values, such as predicting an average rent. A stronger model should clearly beat this baseline, and any gain should justify its added complexity. If the improvement is small, focus on better features or more data. Python code dummy regressor baselines. Compare a real regression model with simple dummy baselines to check whether the model is actually learning useful patterns. The reported metrics show how the baseline and the trained model perform, making it clear whether the model adds value. We import key Python tools for a simple regression workflow: NumPy for numerical computing and Scikit-Learn for machine learning. From Scikit-Learn, we use the diabetes dataset, a dummy regressor as a baseline, and linear regression as the main model. We also import evaluation metrics for mean absolute error and R-squared, along with a trained test split utility to evaluate performance on unseen data. We load the diabetes regression dataset from Scikit-Learn, which provides input features and target values. This data will be used to train and evaluate regression models. The code verifies that the feature data and target data have the same number of rows, so each input matches one target value. If they do not match, it raises an error to signal that the data is misaligned and must be fixed before training or evaluation. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 25% of the data is kept for testing, so the model can be evaluated on unseen examples. A random state of 42 makes the split reproducible, which helps validate performance and reduce the risk of overfitting. We create two dummy regressors as simple baselines. One always predicts the average target value from the training data, and the other always predicts the median. Fitting them simply means calculating those training set values. These baseline models can then be used to judge whether more complex models are actually improving performance. We create a Scikit-Learn linear regression model and train it on the features and target values. During training, the model learns the best fitting linear relationship in the data. Once fitted, it can make predictions on new data and be compared with dummy baseline models. The trained models are now used to predict target values on the test data. The dummy regressors use simple mean and median strategies, while the linear regression model uses the patterns it learned during training. These predictions will be compared to assess each model's performance. A results collection is created to pair each model label with its predictions. It includes the mean dummy regressor, the median dummy regressor, and the linear regression model, making it easy to compare their performance later. The code first reports the Scikit-Learn version to support reproducibility, then prepares a clear performance summary for the models. It goes through each model's predictions, calculates the mean absolute error to measure average prediction size, and calculates the R-squared value to show how well the model explains the target data. Finally, it prints these results in an aligned format, so the models can be compared easily. We evaluate two dummy regressors by measuring their mean absolute error on the test targets, one that predicts the mean and one that predicts the median. The smaller of these two errors is kept as the best dummy baseline, so we can later compare it with the performance of the real regression model. We evaluate the linear model by calculating its mean absolute error on the test data, which shows the average prediction error. Then we compare it with the best dummy regressor by subtracting the linear model's error from the dummy model's error. The printed result shows how much the linear model improves over the simple baseline. This script tests whether a linear regression model performs better than simple baseline predictions on the diabetes dataset. After splitting the data into training and test sets, it compares linear regression with dummy models that predict either the training target mean or median. It evaluates all models using mean absolute error and R-squared, then checks how much the linear model improves over the best dummy regressor. The goal is to see whether the linear model adds real predictive value beyond basic averages. Baseline reporting. Baseline reporting compares a model with a simple benchmark, such as a dummy classifier or regressor, to show whether its performance is truly meaningful. Accuracy alone can be misleading, especially when a model succeeds by predicting the most common class in imbalanced data. A baseline helps reveal whether the model has learned useful patterns or is only exploiting simple data properties. A baseline report should clearly describe both the baseline strategy and the evaluation conditions. It is not enough to say a model beats a dummy method. Explain whether the dummy predicts something like the majority class or the average value. Compare the baseline and trained model using the same data split, validation method, and metrics. If a complex model only slightly improves on a simple baseline, its added complexity may not be worthwhile, but a large improvement suggests it is learning meaningful patterns. Baseline reporting helps make model results understandable and honest by comparing them with simple non-machine learning rules. A model should show value beyond basic assumptions, such as always predicting the most common outcome or using historical averages. This is especially important when simple baselines look strong in stable or imbalanced data, but fail to solve the real business problem. Including baselines should be a standard part of model evaluation. Python code. Baseline reporting. Compare your model with a simple baseline to see whether it truly learns useful patterns. A dummy regressor provides this baseline, and reporting its score alongside the model's score makes the evaluation fair and meaningful. We import key Scikit-Learn tools for a simple regression workflow. The diabetes dataset provides the data, while a dummy regressor gives a basic baseline, and linear regression provides a model to compare against it. Mean absolute error measures prediction accuracy, and the train test split function separates the data so performance can be evaluated on unseen examples. We load the diabetes dataset from Scikit-Learn as a small example for regression. The data is separated into input features and a target value, where the features are used to predict the dependent outcome. This structure prepares the dataset for training and evaluating regression models. Before modeling, the code verifies that the feature data and target values have the same number of rows. This confirms that each set of features matches one target value. If they do not align, the code raises an error to prevent incorrect model training. We split the data into training and testing sets using Scikit-Learn's train test split function. 25% of the data is reserved for testing, and a fixed random state ensures the split can be reproduced. This lets us compare the baseline and model fairly under the same conditions. A dummy regressor can be used as a simple baseline by setting it to always predict the mean target value from the training data. After fitting it on the training set, it makes baseline predictions for the test set. These predictions provide a benchmark for judging whether more complex regression models are actually performing better. We create a linear regression model with Scikit-Learn to learn the best fit line from the training data. After training it on the input features and target values, we use the model to predict target values for the test data. These predictions can then be compared with the actual test targets to evaluate performance. Compare the baseline and linear regression models by calculating the mean absolute error for each on the same test data. The baseline error shows how far off simple mean predictions are, while the regression error shows the model's performance. subtracting the regression error from the baseline error gives the improvement, or how much better the model is than the dummy regressor. The process first checks the Scikit-Learn version to support reproducibility. It then compares a simple baseline, which predicts the average training target value, with a linear regression model using mean absolute error. Finally, it reports how much the linear regression improves over the baseline by subtracting the model's error from the baseline error. This script compares a linear regression model with a simple baseline on the diabetes dataset. After splitting the data, the baseline predicts the average training target, while the linear model learns from the training features. Both are measured with mean absolute error, and a script reports their scores and the linear model's improvement. The expected result is that linear regression performs better, showing it adds value beyond predicting the average. In this lecture, you learn to evaluate regression models using scale-dependent and scale-independent metrics, evaluate clustering results using internal and external metrics, and use dummy classifiers and regressors as baseline comparisons. In the next module, Module 30, we will go over routing inspection.
Thank you for your attention. See you all in the next lecture.